Hey guys, welcome to the second topic. We are officially one topic through. CP2a specifically, resultant forces. Here we go. So, let's start off with a recap question. Difference between the speed of an object and its velocity. This is a scalar and vector question. As we can see, the speed of an object, speed is a scalar, so speed is just the number representing how many meters per second it is, and velocity is also measured in meters per second, but it can be a negative number if you're moving backwards. It's a negative number. So if you're traveling 10 meters per second forward, both the speed and the velocity would be 10 meters per second. If you were traveling 10 meters per second backwards, the speed would be 10 meters per second, but the velocity would be negative 10 meters per second. So that was scalars and vectors. Representing forces, I think, is the bulk of this subtopic. And forces are vector quantities, which means you're going to have a direction and a value, a magnitude, which is the special word for that. And these are represented on an image or a diagram by arrows of different sizes that are usually labelled, like over here, how you've got the arrow, the size, comparison to others, and the number 100 newtons. We can say over here, let's say we've got a car, brum brum, that's a very bad car, but go with it. We've got the forward force, which is about that big, and we can say that that's, I know this is probably not going to be very accurate, but let's go with 100 newtons for now. 100 newtons forward, and that's our, what do you say that? Throttle, let's go. That's our throttle, 100 newtons forward. Down, it's quite small, and we'd label that as 10 newtons gravity. And because it's not super duper aerodynamic, we've also got a moderately big arrow back here that is, let's say, 30 newtons drag or air resistance. Drag. 30 newtons drag, 100 newtons in throttle, and 10 newtons in gravity. And the resultant force from all of that, if we cancel them out and total them together, is kind of a downward-ish facing arrow. And the resultant force is 70 newtons forward, because the 30 newtons of drag takes 30 newtons off the forward force, resulting in 70 newtons total moving forward. So now we've got that out of the way, and we've got our arrows, and representing the arrows, we can have a look at some of these examples. If the resultant forces of all the objects is 0, we say the forces are balanced. If there is a non-zero resultant force on an object, the forces are unbalanced. So, if we can see here, 10,000 newtons of weight, so right now it's just being pulled down 10,000 newtons, but 10,000 newtons of lift from the wings cancels out the 10,000 newtons of weight, so right now it's kind of hovering in midair. 3,000 newtons of thrust from the propeller, so it's going forward, not moving up or down because they cancel each other out, but moving forward at 3,000 newtons. And it's also got 2,500 newtons of drag, which means that 2,500 newtons is taking off of that, which means that the resultant force is 500 newtons forward, because 2,500 is 500 newtons less than 3,000 newtons, so the resultant force is 500 newtons forward. We can also look at this one here. Weight is 900 newtons and up thrust is 850 newtons, so the up and down is 50 newtons downward, because 900 take away 850 is 50, so there's 50 downward, 50 newtons down. Because there are two arrows going this way, it's important to add them together first. So there's 130 newtons total force going forward and 50 going back. So if we take 50 away from 130, we get 80. So the forces on this diver are 50 newtons down, 80 newtons forward. Finally, the exam style question. The forces on a car are balanced. State and explain the size of the resultant force on the car. we can see up here, if the resultant force of all the forces on an object is 0, we say the forces are balanced, which means that all the forces on an object are 0. This could also mean that they cancel out. So if we draw our car here, a bit better this time. Car. The forward would be exactly the same as the backward. It's not likely that they'd be the exact same drag and thrust, so we can just say 0 newtons and 0 newtons, forwards and backwards, so they're the same. And I'm not sure how you'd get up thrust on a car, but you do nonetheless. So let's have a little arrow going up and a little arrow going down, the exact same size because they're balanced and they're 0 and they cancel each other out. So let's say 100 newtons of gravity and the same 100 newtons of upthrust. Upthrust is almost definitely not the right word, but it's the only way to describe what the balance is here. Because the forces on the car are balanced, 0 and 0, that's a balance, they're cancelling each other out. 100 newtons, that's a balance, they're cancelling each other out. State and explain the size of the resultant forces on the car. We can say all forces are the same as the opposite forces. So the backward 100 newtons is the same as the forward 100 newtons, and the downward 100 newtons is the same as the upward 100 newtons. So all forces are the same as their opposite forces, backwards, forwards, upwards, downwards, same as their opposite forces, and cancel out to result in a force of 0 newtons, that's going to go off the page, in any direction. And if I go back to here, I can just press enter and that sorts itself out. Right, you can see here all forces on the same as the I think you would be offered the space to do a diagram, but we can mark this now. Ignoring the diagram, all forces are the same as the opposite forces, that's one mark, and cancel out to result in a force of 0 newtons in any direction, that's our second mark, which gives us a total mark of 2, so that's 2 out of the 2 marks offered on that question, and that is all you need to know about resultant forces. I'll catch you in the next one. CP2b, goodbye, and I'll see you later.